This is section 14.2, part C. We're now going to look at line integrals of vector fields in a little bit more general way. In these next couple of videos, I guess I should probably say, we'll look at something called circulation, and then we'll look at another, still a vector field line integral, but something called flux. This is going to generalize the ideas that we saw in the last video when we were working specifically with the concept of work. So you'll probably recognize that line integral as the line integral that we developed for the concept of work. But we're going to look at it without exactly thinking about a work, but in a little bit more general sense right now. The integral over a curve C of the dot product f dot t ds. Again, what is that integral really measuring? So here's my curve C. Notice the direction of motion here. And one thing I do want to point out is that the direction of t is consistent with the direction of motion. Since we're moving towards the right, notice t points to the right, not the tangent that would point left. Here's the vector out of our vector field f, right? There's lots of vectors out here in the vector field, but this is the one that applies at that specific point. And f dot t is the magnitude of f cos theta. Remember, that's the magnitude of t is in there, but it's just one, so it's not written. And that really measures the amount of f in the direction of t. So how much of f is in the t direction? This next picture helps us to conceptualize that just a little bit more. Let's start by looking at this point right here. Here's our vector f. There's our vector t. And notice that if I were to project f onto t, just drop a perpendicular there, some of f does point in the t direction. F dot p would be positive in that case. It's a positive contribution to our overall line integral. Compare that to this point over here. Here, if I were to drop the perpendicular from f, it would actually point in the opposite of t direction, just slightly. It's not helping, it's not pushing us in the t direction at all. It's actually slightly pushing us in the opposite or wrong direction. F dot t here is going to have a negative contribution to the line integral. So if you start thinking about this dot product f dot t as a measure of how much of the force vector f is pushing in the direction or along the curve, that's going to be a really helpful interpretation as we move forward. So let's think of this whole integral as measuring how much of f helps push us along the curve. This concept has a name. It's called the circulation. It's how much of f is circulating us or pushing us along that curve. And this little, or capital gamma, is what that is, Greek letter gamma, is the variable that we use to represent circulation. So we'll be starting to call this the circulation integral. And again, conceptually, it's how much of f helps to push us around that curve. All right, as far as how it's evaluated, there's not going to be anything new here. I'm just going to take probably about 45 seconds to review very quickly what we already saw for work, because the concept is the same, even if we're interpreting it slightly differently. So again, t is a unit tangent vector. The tangent vector would be r prime. And to make it a unit vector, we would divide it by its magnitude. Arc length is the distance along the curve. This is true, but I wasn't using it. I was saying that means that ds dt, the derivative of distance, is speed. but another way to write speed is the magnitude of the velocity vector. So ds would be r prime, magnitude of r prime, multiplied by dt. And then when we put those pieces together, our integral becomes f dotted with t, r prime over the magnitude of r prime, times ds, magnitude of r prime, dt. And when we simplified all of that, canceling out the magnitudes, we just get f dot r prime dt between the endpoints a and b. Right? So no surprise there. Before we go on and evaluate a few more of these things to start to see some of the intricacies of this kind of stuff, I do want to just talk a moment about notation. I think I warned you last time that this was coming. Unfortunately, there's kind of a lot of ways to write the line integral of a vector field, and I just want you to be able to recognize all of them, even though we'll actually always use the same one to actually evaluate. So if I've got a vector field f, and I probably should have an arrow over that, that's a vector field f in 2 dimensions defined as f comma g. The curve c parameterized in the form x of t, y of t from a to b. Then this circulation integral f dot t ds can be computed, as we just saw, as f dot r prime dt. You may remember from last time that I said another sort of shorthand way of writing that was f dot dr. So you may see that from time to time as well. And then there's one other way that you'll often see this written. If I were to actually write this out, f was f comma g, dotted with r prime, which would be dx dt, dy dt, times dt. I could actually let the dt's sort of cancel out algebraically. And so, doing the dot product, I would end up with f times dx plus g times dy. G times dy. And that's another way that you'll commonly see these things written. So, if you see any of these forms, they all mean the same thing. They all mean the circulation integral. And no matter which of those forms I see or I'm asked to find, I'll always do the problem this way. They all mean the same thing, really all 4 of them. But this is by far the most convenient representation for me to actually evaluate the integral. So again, no matter which of these I'm asked to find, that's the way I'm going to do the problem. The same various ways of writing it exist in 3 dimensions. It's just that f would have 3 components now for the vector field, and c would have 3 components for the parameterization. We would still be able to write this in the same 3 original ways. It's just that when we get to the 3rd way, we'll have that extra component. So we'll have not only f dx plus g dy, but we'd also have the h dz. All right, so that's just notation. Let's go ahead and in example 5, let's find one of these circulation integrals. Notice I've given it to us in the form f dot t ds, but I'm going to do it this way. The vector field this time is minus y x, and the path c is going to be the upper semicircle of radius 4, centered at the origin, And I should have included this information, so if you would add that, please. We're going to traverse counterclockwise. So here's my vector field. Let's go ahead and work with the path R, or C, which we're going to parameterize as R of t. It's the upper semicircle of radius 4, centered at the origin, and we're going around counterclockwise. Typically, parameterizations are easiest when I let x equal t, except for the special cases of the circle or ellipse. Those are best done, remember, with sine and cosine. So I'm going to parameterize differently than I have been. I'm going to use sine and cosine. Since it has a radius of 4, r would be 4 cosine t, for sine t, right? And that's going to automatically make this go counterclockwise. Remember, if I want to go clockwise, I can reverse those. From this, I can get my r prime, negative 4 sine t, 4 cosine t. And I can also write the f. Remember that f is minus y comma x. And as soon as I've defined the r, I've defined the x and the y. So I'm just going to plug those in to that f. Minus y comes first, so that would be minus 4 sine t, comma x comes second, that's 4 cosine t. I wanted the upper half circle, so my t values this time go from 0 to pi. All right, so that's all of the information I need to set this up. I'm going to say that instead of evaluating f dot TDS, I'm going to go back to my favorite way. I'm actually going to go with f dot r prime dt. I'm just going to plug in all of this information. Our integral goes from 0 to pi. Put in my f. Dotted with my r prime. dt, squeeze that in. And doing the dot product, I would have 16 sine squared t plus 16 cos squared t dt, which of course is a beautiful trig identity. If I factor out the 16, I would just have sine squared plus cos squared, which is 1. So that's just 16. Integral is 16t from 0 to pi, giving me an answer of 16 pi. All right, I'm actually going to squeeze in an extra example here. I'm going to continue to use the same vector field, but I'm going to use a different path. And then I'm going to come back to this one, and we're going to compare the answers and talk about why geometrically they hopefully make some sense. So this is not in your packet of notes. You might want to grab a spare sheet of paper or something, and let's take a look at what I'm going to call example 5.5 or 5.5. So I still want us to evaluate the same, what we're now calling a circulation integral, f dot TDS. Same vector field, f is still minus y comma x. But instead of working on the upper semicircle, this time our curve, our path, is going to be y equals the square root of x from 0, 0 to 4, 2. All right, so let's start with C. Y equals the square root of x, starting at 0, 0, ending at 4, 2. So we're going this way. And once again, I have to start by parameterizing. So in this case, just letting x equal t is probably going to be my best bet. And that means y would be the square root of t. Since x is equal to t, and the x values go from 0 to 4, that means my t values will go from 0 to 4. R prime, my derivative is 1, and 1/2 t to the negative 1/2, or 1 over 2 square root t. And then my f, again remember, once you've defined r, you've defined the x and the y. So I plug those in to f. First component is supposed to be minus y, so minus the square root of t. Second component is x, so that's just t. All right, that should be everything I need to get my integral set up. So even though it says f dot TDS, I know that I always evaluate it as f dot r prime dt. Don't want that ds integral. All my variables are t's. In this case, my t's go from 0 to 4. I'll put in my f, dotted with the r prime. And doing the dot product, I'm going to get a minus the square root of t plus t over 2 square root t. A little algebra here. Let's see, that would be a 1/2 t divided by the square root of t is the square root of t. And so I have negative 1 square root t plus 1/2 square root t would give me negative 1/2 square root t dt. And that's not difficult to do by hand either, but I went ahead and plugged that one in the calculator. I got negative 8/3 when I did for the value of that integral. All right, here's what I'd like to do. I'd like to talk for a moment beyond the mechanics of why it is when I calculated this integral, I got a positive value, 16 pi, a fairly large positive value in fact. And this one, I got a negative value. In order to do that, I need to take a look at the vector field, negative y, x. You may not remember, but way back in section 14.1, which seems like a long time ago now, we looked at this, and this was that rotational vector field. So I actually plotted that using Maple. Here's the rotational vector field. In an example 5, that was the one where C was that upper half circle. Of radius 4. If I go over here and actually try to plot that, there's 4, 4, negative 4. We're traversing counterclockwise. What I'm hoping you can see here is that if I'm trying to go from here to there along that semicircle, this vector field is giving me a lot of help. In fact, it couldn't hardly help more. It follows my direction of motion perfectly. And so my integral, the circulation that we calculated, was 16 pi, a fairly large positive number. The vector field is giving me a lot of help as I move along that path. Now compare that to the second one. Same vector field, so here it is again. In example 5.5, as I called it, our path here was the square root function. y was the square root of x, and I think it went from 0, 0 to 4, 2. When we did the circulation integral, we came out with an answer of negative 8/3. And look at what's happening here. I'm trying to move this way along the path, but what's the vector field doing? It's not helping me at all. In fact, it's working against me, right? I want to go this way, but the vector field's pushing this way. Look at the direction of the arrows. That's why we ended up with a negative circulation. In fact, if I really wanted to move along this path, I would have to put energy into this system to move here. The system would not do the work for me. So that's the difference between a positive circulation integral and a negative circulation integral. Does the vector field help you move along your path, or is it actually working against you as you try to move along that path? All right, we'll pause there and come back and do just a couple more examples.